So इसका like the data path, and if I draw the like, because the synchronous design, everything is happening on pause edge of clock. Okay, so there is a clock. So you got to have plan that first you need to, for example, read value in R1 register in this clock cycle. Okay, and because you need two values to compare, you read another value in this clock, R2 value. And once you have R2, this will do the comparison and you have the result of the comparison. So in this clock cycle, you can store this value, both the values, in R3 and R4 register. Because comparator has two inputs and two outputs, so you store this in R3 and R4 register. Now in this clock cycle, so we are not trying to optimize and make it, just first attempt, I'm just saying that how it should basically run. So I want to store R3 in my memory. So R3 has to go in the memory because there is only one bus where I can only read or write. It's a single port memory. And then I go and do the R4 in the memory. Okay. And here again, I restart by loading a value in from memory into R1 register. So kind of my states are, first I need to have a state where I read R1. Then I need to have a state, because every cycle is a state, I need R2. And it'll definitely, once R2 and RT, as it is a combinational circuit, so it'll do the comparison. So I assert to write values in R3 and R4 register. So this and this value, we may say this is the large value L and this is the small value S. So the large value has to be large into R3 and the small value into R4 register. And then so this is cycle number 2, the state machine has 2, and 3 is that I assert the write enable signal into R3 and R4. And then in cycle state number 4, I write R3 into memory and I write R4 5 into memory, and then I start again. So as we know that the loop starts by having the address. First, it requires, like the way we were doing it is this address and then this address. So these are the two that needs to go into R2 and R1 register. And then in next cycle, we need to bring, so we store the larger in this memory and the smaller in this memory, in this part of the memory. Okay, the smaller value will go here, larger will go here once we are writing. So R3, we need to write it here. R3 is to be written, the R3 is the larger. So larger will go here and smaller will go here. Okay, and the next cycle, again, we need to have these two values. And again, once we store, the larger will come here, smaller will go here. Then again, we need, so similarly, so we have to read, we need to have a register, which is, it can start from the above as well and push the largest value or the smallest value to uh, to the last. So we can equally start from I and J. So there is an I register, I value counter, and there is a J counter. Okay, which primarily would have that how it is going to generate the address. And then we need to know that how many times and all of that. So, but let's just do the data path, which is beside this, that I, J, everything, we keep it outside the data path. So data path currently is this. So in order to, and this is our overall design. So let me from here start writing what all I need to do. So I say generate a module that shall have the following. Okay, so first I would like the generate a module. I write register transfer level Verilog for a module that should have the following. Okay, so I want, first thing is that it should have a 16-bit wide, let me say 32 deep memory. Okay, so instead of 16 deep, so that just to have a difference, so I'm saying 32 deep memory. This first thing I want it to have. Then I want it to have 4 registers, R1, R2, R3, R4, and I can say 4 16-bit registers, R1, R2, R3, R4. A comparator that compares the value in R1 and R2 registers and stores the results in R3 and R4 registers. Larger registers, larger value in R3 stores the result and store the results, stores the large value in R3 and a smaller value in R4 register. Okay, so this is done. So then I want that the module shall have the following inputs. I want it to have clock as an input. I want it to have address of memory, call this address. So clock is 1-bit input. 1 bit clock. Address is going to be, because it's 32, so 4 bit. 2, 4, or 5 bit. 5 bit address of memory address, and because you will be writing into the memory 16 bit data in, and you will also be reading 16 bit. These are the inputs. So you have a clock, you have address coming in, you have this, then you have enable 1 bit enable signals for R1, R2, R3, and R4 registers. 4 bit enable signals for write enable signals. Write enable signals for R1, R2, R3. So we want enable, 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 enable. And who is sending these enable signals? Obviously the controller. That's why I want them as the input. And to write in memory, also want to have address here, 1 bit write enable to write in the memory. Okay, whatever is on the bus, we want that to go in the memory. And because write enable to write, and you can have multiple to write data into memory. Okay, so we can have multiple signals. Similarly, 1 bit write enable signals to write R2 and R3. Sorry, R1, R2, R3, and R4. R3 and R4 in memory. Okay, once you say R3 goes to memory, R4 goes to memory, you want to say the data which is coming out goes to memory. So we have an address, you go to a given address, and then also you need to read. Yes. So these are all our 1 bit read signal. So address, 5 bit address of memory, address memory to write in memory. So this is for writing, and then you need to have a reading as well. 1 bit, or I think you can just simply have 5 bit address to read from the memory in R1 or R2 register. And this is address read. And the following outputs. Output, I think only you need a 16-bit data out. So once you're reading, you just assert address, and it'll just keep giving you out. So I think pretty much this is how you create your prompt. And let's try to generate this code for. So I've been trying to do this. So let me just go and say, okay, so I copy it here. Sorry, that's because of the word. Generate RTL variable code for a module, for a data path module. Data path module of a state machine-based design that shall have the following: 16-bit wide, 32 deep memory, 4 16-bit registers, a comparator that compares the values in R1 and R2 registers and stores the large value in R3 and smaller value in R4 registers. The module shall have the following inputs: 1-bit clock, 5-bit address of memory to write in memory, address write, 16-bit data in to be written in memory, 1-bit write enabled to write data into memory, memory on address W, 1-bit write enable signals for R1, R2, R3, and R4 registers. 4 1-bit write enable registers. Signals for this: 1-bit write enable signal to write R3 and R4. 2 1-bit write enable signals to write R3 and R4 in memory. 5-bit address to read from the memory in R1 or R2 register. Address R at register at memory location address R, and the following output: 16-bit data. Okay, let's now generate. Oh, I need to tell it few more things that I have not. Let me also, this is fine. On assertion of, enable R1. This is quite a work because of the obvious reason that what we are trying to achieve is a pretty complex design. So I forgot that on assertion of R1 enable, the value pointed by address read shall be latched in R1 register. Similarly, on assertion of R2 enable, the value pointed by address read shall be latched in R2 register. And on assertion of here 1-bit signal, this 1-bit write enable signal write R3 R4. Assertion of write R3 R4, the output of the comparators large and small shall be latched in R3 and R4 registers. Okay, so this is all what we want to do. and then is address to, yeah, I think this is pretty much what I wanted to do. So code for a datapath module. So you need to do the design. Let's do a fresh start. So you say, I don't know why it's so. So pretty much clock is fine, 5-bit write, address write is fine, 16-bit data in is fine, write enable is fine, 5-bit address read is fine, write enable 1, 2 is fine, wire write R3, R4 is fine, and output wire 16-bit data out is fine. So ports are okay. Memory is fine because it is 15 down to 0, memory 0 to 31, so it's 31 deep. So this is fine. Internal registers R1, R2, R3, R4 is fine. 16-bit registers. Two values which are wire, larger, smaller is fine. Assignment is okay. This is the comparator. R1 greater than R2. Then R1 goes to larger, or R1 smaller. It has to be, yeah, so it has reverse. R2 goes to smaller. So this is fine. Pause edge clock, data in goes to the address memory. This is very good. This is fine. And then this is the read, that the address read memory goes to data out is fine. And now is the pause edge of clock. If write enable is asserted, whatever address is here, it goes into R1 is good. Else if write 2 is asserted, if so whatever its address goes to R2 is good, so this is good. And then if write 3, 4 is enabled, larger R3 goes here and smaller R4 goes here. So this is good. This is pretty much what we wanted to do, except now what I have not written here is, so this is very good actually. I'm really amazed. What I have not written is on write write. So there are to be two more signals. Where is the value of R3 shall be written in memory pointed by address address read on assertion of write R3. Similarly, value in R4 shall be written in memory pointed by address R. Same bus on assertion of write R4. Define 1-bit write R3 and write R4 as well. So this is what was not there. So I can ask it to add it here. So let me just add the following in the module. So So write R3, write R4, it has added, which is good. This is fine. Data in. Now this is very good. Now write R3 asserted, so it writes R3, or write R4 asserted, it's write R4. So it is reading. Once somebody wants to read, it is doing that. This is fine. And then the address and address R1, R2, larger, larger, smaller. So I think this is very good. Pretty much the
Sir,
design. GG.
sir, why do we have multiple always blocks here? Are they needed?
It's fine. You can have as many always block as you want to. It does not really hurt. As long as they are assigning to different left-hand sides, that is fine. So it's just for the uh, easy reading that you have multiple always possess block. Okay? They
Okay,
must
sir.
not be assigning to the same variable. Means this is R1, R2, R3, R4. So that's why it is fine. So you can have as many always block as you may want to. So this seems like a good way. And what we have learned in this is that first you need to be clear that what you are going to do. Okay. So you need to focus on your design, not on an RTL level. So I just keep emphasizing that you design at register transfer level. You got to know where your registers are and any computation, because here we are only doing only have a comparator which is doing the computation, so it is fine. So you need to know that the combinational block is just the comparator, and then your registers are here, 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 and this is your memory. And your memory, first you put an address, you read a value, goes in R1. Then you put an address, and this is what you are going to do in controller. In this, and the controller, I would like you to do it yourself. And but this is how the controller will work. First, you need to assert read R1. Okay, read R1, and you got to have an address, and then you need to just an address, a valid address, which will, if you are starting like this, so this first address is what you give it to this in the first cycle, and assert write R1. Then in the second cycle, you assert read R2. So two values, it'll compare. In the next cycle, you assert write values R3, R4. Then you assert write R3. Then you assert write R4. So like this, what I have shown here as well, and what is there in the code as well. So you will find out that the appropriate control signal would make your all these procedural block with an if statement would act accordingly. That whatever you intend to do, they will do that. So this is good. So we know how to convert a fully dedicated architecture into a time shared architecture, and we have learned the data path and the overall design, where now this controller is going to control and send most of the input signals, which we have defined here. Means it will say now write in R1, write in R2, write in R3 and R4, write in the memory, give the address. So all these the will be generated by the controller, and outside the controller, the module which actually is going to use this sorter would first write it into the memory by asserting a write signal, which we say address write. So asserting address write, whatever is here would get into the memory, get into the memory. So you have all these going into the memory. And this is what the code I generated earlier. And once I was checking it myself, that how can I kind of generate this code. So this is interesting that how the code can be generated. And I also have like two different addresses. One address is from the outside who is writing data into data memory. If write enable is asserted, filling the memory, and then you start doing whether you want to write in a register A, register B, register C, register D. So all of this is here, and then is uh, the state machine part, which I want you to kind of generate. And this will be an exercise where it is sitting in idle. Once nobody is asking it to do anything, it will remain here. Okay, idle state machine. And once it says filling the memory, with some external body is just filling this memory, and once the memory is filled, it will say go sort. Okay, so once you say it says go sort, you come here and you read first value in A register, and so here you have to generate all the appropriate addresses, which is one address, which is our apparently J variable with the address. So J is which start from 0. And then you are incrementing, then you say write. So address will now be the J variable, which will be now 1. And here I will also be 0. Okay, then you say comparator will automatically. So there is nothing, because whatever is A and B, comparator is always comparing. It's a combination logic. It is active all the time. So you do write in, remember, so this is read in R1 from our code generation perspective. This is read in R2. And once you have read, in the next cycle, you assert to write in R3 and R4 register. So it is being written. Okay, so you assert this, and next cycle you say write R1, and here you need to write in the smaller value goes into 0, larger value goes into 1, and write B, smaller values goes into 0. So in somehow, you need to figure out this. And then you go here again. You have incremented J. Now J is plus plus. So J was 0. So J will become 1. Okay, actually, these are the addresses. I should not say it is J. These are the addresses which are driven from J. So you say J plus plus, and also check if J has not hit n minus I, which is the total length minus I, because n minus 1. This is how the sorter works. So this is something you got to keep checking. If it is equal to 0, then you need to increment I plus plus, and you need to initialize J back to 0 or J back to I, starting from I, something like this. It depends on how you are actually. Where J will be 0 because largest value you are putting it in the end. So J will be 0. So some of these things, and then doing this, and checking. And once your I collapse, like you're done with all the I, and for that I, all the J, so you are done, and you generate a done signal. Okay, and say generate signal and get back into idle mode. So this is how the state machine is work, and the overall architecture will be something similar. So very intricate kind of a state machine. So the controller, and a controller has, this is the data path, and the signals which are coming from outside, in and out, and the signals which the controller is sending to the memory based on some of these I's and J's. And This is how the whole thing is going to work. So pretty intricate, complex design, and I believe that this design can be generated with if you are very focused and you have actually broken down your design and you precisely know that this is how your registered transfer level hardware should work. If you don't know that and you try to just generate a code which can sort using a comparator, okay, so you can try that as well. So perhaps it will be very hard for the tool to figure out what exactly. So if you say generate RTL Verilog code that can sort an array of 32 numbers, 16-bit 32 numbers using only one comparator. Okay, so very broad statement that you have given. So first it has instead of having one memory, it has generated two memories. One will have this, then is the sorted array, ij temp minimum index minimum value, is started creating an array, idle find minimum swap done state. So ij minimum index minimum value state idle done, else if case state begin idle initializing ij min index sorted array. So it seems like first issue is that you cannot read two values from the memory which you are comparing. So where is the comparison? So you need to find out where is the comparison. So I think you can try doing this as well, but I was seeing a lot of issues if you just give a very broad statement it to. So it is, for example, here the complete array is saying array in goes into sorted array. So this cannot really happen in Verilog, that a complete array in a single cycle that you copy into another array. So this is something not RTL. Then he has just one value. What he's trying, I think, is trying to find out the minimum value and having something initialized, always reading one value. So it's not swapping, so to say. But if it's not swapping, this will not work. Because you have to run this again and again and again. So perhaps we can see that this code, whether, but you have very less control on this code because you got to understand what it has done. Apparently, just having find minimum swap value cannot happen in single cycle. The states cannot happen in single cycle that you swap and then you are done. So it has only idle state. So here is what it is doing in idle state is that apparently just sitting there. Then find min, it has minimum value it is comparing, and then storing this and remembering the index. And then it has swap. Swap is where, so this is another problem that you cannot write in a single cycle. So you cannot write into uh, in a memory, you cannot write two values at the same time because we are assuming a single port memory. So though perhaps the code may work, but this definitely this will have implications on the hardware. Still, we can perhaps try making it work, but I would like us to have like this approach where you design a data path and generate code for the data path, and then generate a state machine which is only sending control signals that you will have more control, though you will have more deliberation in your design, but the design will be in your control, and you will be able to do more with the design. So then there are like several other simpler examples where the controller is very simple. Like you want a bit serial architecture, and there are 8 bits in these three registers. Or every cycle, just one bit will go add and carry. You are going to reuse the carry for the next bits addition, and then you are also subtracting minus c. And so these type of designs where you have very simple controls, it's a counter which is just running for eight times. So you start and there's an 8-bit counter, and after 8-bit expires, you get an output. So bit by bit you are sending the output, or it could be two bits together, it could be four bits together. So it could be a bit serial, or it could be a word serial, depending upon how many bits you want to kind of process through this adder and subtractor. And those many bits are to be then sent to these registers, which is shown here. So, so these are the type of designs. Similarly, you can have shift and add multiplier as well. A multiplier will take n cycles. So like we do multiplication, so you have bits here and bits here. So you can look at this bit. If this bit is 1, so you have the entire number as a partial product. If this bit is 0, you have 0. So this bit will decide whether you will have 0 or you will have the entire multiplicand as a partial product. Okay. And next time, once you are generating a bit, you got to shift it to the left. So that has to happen. And that once you have this, instead of shifting this, it shifts this value to the left, to the right, what you have generated as a partial product. So it's just keep shifting it to the right. So it's a little intricate design, but what it shows is that a time shared architecture where you have a multiplier, and multiplier will take 16 cycles to multiply a 16-bit number. And if you have 16 cycles, it is around an adder. You may say, okay, I'll use it, but sometimes you don't get into, the bit serial and these type of multiplications and additions. And this is only very rare case where you say, I have a lot of cycles and a lot of multiplications, so I don't mind putting even a single multiplier in my design. I convert it into fixed point, and then I have these type of multipliers, which are called sequential multipliers or shift and add multiplier. It may able to generate. I don't know. Let's see if it can generate. And this is the last thing I'm going to do, and then we'll take a break. I've been teaching since morning. This is my second 3 hours lecture. So I say design, generate RTL Verilog code for a 16 by 16 bit shift and add multiplier. Add sign by sign, sign x by sign X multiply. It'll be interesting to see if it can actually, yeah. Yes. Yes. Kind of. Kind of. It has kind of generated. It is shifting and adding, and though because we have not actually gone into that how we intend the architecture to look like, it has done that. So there is mm, partial products that are being generated. There's a multiplicand and multiplier register, and so it's kind of doing it. So thank you very much. Inshallah, next
Sir,
exam, Gigi.
sir, just wanted to get your opinion on right now with the sorting example, we first made a fully dedicated architecture. Now we are translating into a timeshare architecture. Do we follow the same kind of approach when doing designs in general? Like we make a fully dedicated architecture, then we translate to timeshare, or we can directly
No, no,
do that as well.
no. You need to find out the budget that you have. Okay. So if you have only one cycle available for sorting, then you got to make a fully dedicated. But this is not a practice that you first make a dedicated architecture and then don't waste your time in making a fully dedicated architecture. Find out the budget and learn that this is how, if you're going to fold or time shared, then you need to have just right from the start make a time shared architecture.
Also, sir, right now, when translating our design from fully dedicated to time shared, we basically sort of traded off the computational blocks with the memory, and there is some also logic for the controller. So, with regards to like estimating cost, is the net effect the same as having
No,
multiple
no, no, no.
computational block?
Dedicated, if you are making a 32-bit sorter, so fully dedicated architecture would have 31 plus 30 plus 29 plus 28, till one number of comparators. Okay, it would have a humongous, huge combinational cloud. Then you have to add pipeline registers, and so that would not be really a good design. Once you compare, time shared architecture will have very small area as compared to a fully dedicated architecture, and will be very effective.
So just one last thing. Just want to get your opinion on this for doing this sort of an exercise when we're generating RTL code for this timesheet or any sort of this architecture. Is it wise thing to do to sort of like what we did in the algorithmic examples? Like we had a Python model and we just decided to do everything in the Python domain and then we translated into RTL. Can we do something similar here as well, or is it not
No,
as
no,
well?
no, not really, because here Python is only once there are a lot of computations happening. Here, the only computation is a comparison, so you don't need to generate Python code.
But what if I want to sort of, if I have a complex design, let's say not just this
Yes,
comparator.
then like once we were doing the SHA-256, okay, there I would prefer that there's a lot of logic that goes into the combinational cloud. So that's why I said if you have something where there are a lot of computations that are happening, you do it in Python and bring the whole thing into Verilog, but not where you have only one comparison. So uh, that will not be very useful to have something, because all the intricacies here are relating to your register transfer level design, a single port memory. So the design challenges are very different. So there's no point in doing it in Python.
So just I'm asking from a perspective, assuming that I have a very like a complex design, let's say
Then you
sharp.
then you should always first design your algorithm in Python.
Yeah, but what about the like if I have a huge design space where I want to explore different sort of controller programs and I want to also see what the sort of changes I make to the data path and how it affects my overall design. Like if I want to do some design exploration, would it be wise to keep generating very log code, because very log debugging very log code is like more tedious compared to Python? Wouldn't it be wise to have sort of like a Python model for
No,
controller and data path?
Python model is only to have the algorithm written in Python, like deep this CNN. So you generate it in Python, and then you let it at the detail level. Like Python must not be using any function, having convolution loops and everything, so that you see the code, and then you can just copy the computation. But doing these design space exploration in Python is not possible, not even possible. Okay, so you have to do this in the design, not in the Verilog. Okay, the way I have done it, like you first spend a lot of time in the design, and that's what I have been telling right from the start. Focus more that how you do the architectural design, and only once you have to come and generate the Verilog code. So the design is important, that how you design your architecture, and that is driven by the budget that you have, that in how many cycles you have to do it, and do it on paper, do it at RTL level, do it controller and data path, and then just generate Verilog code and test it.
Okay, sir. Thank you.
Okay, Ji, and thank you.